Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to this webinar, Bridge Monitoring with Distributed Fiber Optic Sensing. And we're very pleased to have with us two of the people who have really done some very creative work on this, Werner Lienhart and Lisa Strasser from the Technical University of Graz. They have done presentations in the past, so it's always interesting to catch up with them. Sort of what are the potential for using sensing with infrastructure. So we look forward to hearing your presentation.
Yeah, thank you very much for the introduction. It's a great pleasure for us to give this webinar today and tell you our experiences in bridge monitoring and especially show you the potential of distributed fiber optic sensing. Before we start with the bridge monitoring itself, just a few comments about us. So my name is Werner Lienhart. I'm head of the Institute of Engineering, Geodesy and Measurement Systems here at Graz University of Technology.
Hi, I'm Lisa Strasser.
Yeah, and Lisa is leading the DAS, so the Distributed Acoustic Sensing group here at the Institute. So what we do, we focus on monitoring of superstructures like bridges and natural phenomena. And for this, we use fiber optics since more than 20 years. So you will see a lot of different examples of bridge monitoring that we already did in the past. And what you're also gonna see is that fiber optic sensing is a great tool, but sometimes you need some additional sensors in order to deliver a complete solution. Regarding fiber optics, what we also want to show is that in many aspects, it's already a very mature technology. And that was also the reason why a few years ago, we founded our own spin-off company, who's also offering monitoring services with distributed fiber optic sensing. So our goal in the end is we want to develop, calibrate, install, operate, and maintain monitoring systems for civil infrastructure. So we did a lot in tunneling, we do a lot in large concrete dams, we do projects in bridges, and also earth structures, like reinforced earth structures. And the final goal is to have a fully automatic warning, alarming, and reporting system. By doing so, fiber optic is one of the great sensors, and this belongs to the group of embeddable and surface-mounted sensors. So here we know directly, we are close to the structure, we know directly what's happening on or inside of the structure. But very often, we also want to get a broader understanding how the structure is changing overall, and therefore remote sensing techniques are very useful. So here we're using drones, GNSS, total stations, radar interferometry, and a lot of laser scanning. Where do we do projects? We are based in Graz in Austria. So Austria is Central Europe. We also have a lot of different projects in this area, but we also had projects abroad. And regarding Central Europe, we have installations in our neighboring countries, so Slovenia, Germany, Switzerland, Czech Republic, Italy, but we also do a lot in Austria itself. Regarding fibers, we have used fibers, embedded them into landslides, we have put them on earth dams, we have used them in concrete arch dams, we have integrated them in reinforced earth structures, we do a lot in piles, we applied them to pipeline monitoring, use them for anchor monitoring, for tunnel, shotcrete-based tunnels, but also tunnel boring machine constructed tunnels, a lot in rail, and finally, the topic of today's presentation, bridges. And now it's really, let's say, a window of opportunity to apply modern sensing technologies for bridges. It's really exciting times because on one hand, we have the problem that our structures, those bridges are deteriorating. And a lot of them are at the end or even beyond their design lifetime. And this is a special problem in many Western countries. What you can see on the top right is the construction activity regarding bridges in the US, in Japan, and in Europe. So most of the large bridges have been built in the late 60s or in the 70s. And now, assuming a typical lifetime of a bridge, between let's say 50, 60 years, we now come to the end of their lifetimes. And what we want to do, we want to still keep them in service in a safe way. So therefore monitoring is needed. Furthermore, we also want to support the bridge owners in the maintenance program. So here monitoring data can be used for predictive and condition-based maintenance. And finally, if possible, we also want to extend the lifetime of the structures. And this saves money, but also reduces or postpones our CO2 output. So there are several different reasons for bridge monitoring. And what you're also going to see is as soon as those bridges are being replaced, there's the chance to embed something in bridges who are built new. We use distributed fiber optic sensing in today's talk. And just remember, with distributed fiber optic sensing, we use one single fiber as sensing element. And now, depending on what technology or specifically what instrument we connect to that fiber, we can either measure thousands of strain measurements along that fiber, or we can measure thousands of temperature readings along that fiber, or we can realize thousands of vibration or acoustic microphone sensors along that fiber. So everything with one single fiber. And this is especially the topic of today's presentation. If you make one step deeper, what is distributed fiber optic sensing and how does the signal look like? So we couple a light pulse into the fiber and work with the backscattering element. So in the end, we send in a wave with usually about 1550 nanometers or a pulse, and what we get back is most of the energy at the same wavelengths. So that would be Rayleigh backscattering. But we also do have other backscattering effects like Raman and Brillouin. Raman is very useful for temperature sensing as it is not sensitive to strain or almost not sensitive to strain. We are not focusing on this. What we are focusing here today is Brillouin and Rayleigh sensing. So with Brillouin, we have a certain Brillouin frequency shift from our core wavelength to the Brillouin frequency, and we can observe now how that shift changes when temperature changes and or strain changes occur. However, that's a very nice technology, but the measurement time is usually rather slow. Then we also have Rayleigh backscattering, and this enables either high resolution strain sensing on short lines or distributed acoustic sensing on very long lines. But now let us take a look what long and short and fast and slow actually means. So what you can see here now is a typical situation of the characteristics of the different measurement principles. As I said, DAS, so the distributed acoustic sensing, works over very, very long ranges. So this could be 80 kilometers or even longer than that. Here we measure not strain directly, we measure strain rate. And this can be done with several kilohertz, however, with rather coarse spatial resolution of about a meter or several meters. On the opposite side, we have high dynamic fiber optic sensing, so the far right column of this table. This is based on Rayleigh sensing, very often works only on short ranges, but with a very high spatial resolution of better than a millimeter in best cases. And in between, we also have then the Brillouin sensing, also goes for very long ranges, has a spatial resolution usually in the range of a few decimeter, however, it's rather slow. So here measurements take seconds or even up to several minutes. So here we can only observe static changes. And all of these technologies, so all these four different types, will be seen in this webinar in different applications. Before we go now to full-scale real bridge, let's take a look into the laboratory. So what you can see here is, let's say, a simulated bridge. So this is in the end essence just a metal beam, but fully equipped with sensors. So here we have several accelerometers mounted to that beam. We have image targets, so those are the black dots. We have a prism for total station measurements. We also have laser triangulation sensors applied here, and this is important now, one fiber line. So there's one single fiber optic sensing cable, first going along the top part of the beam, turning around and going along the bottom part of the beam. And these short ranges we can measure with a high spatial resolution, and what's definitely sufficient for this case, measure with a rate of up to 50 Hertz. So we get dynamic strain readings every 2.6 millimeters along that metal beam. We want to do that dynamically, so let's see how that looks like. In this case, we just make a very simple setup. We just put that beam down and let it vibrate. So what we can see here is that we have on one side positive strain, on the other side negative strain. So here we can see the mirrored behavior of the bottom fiber and the top fiber. That specific shape of that curve is a reaction due to the type of bearing the situation that we have. So in this case, the left bearing is fixed and the right bearing is a roller bearing. So just by looking at the shape of the data, we can say, for instance, if bridge joints are being blocked or not. So we can see if the bridge can move freely or if one joint, for instance, does not work properly anymore. Again, so that's the situation that, or the result we achieve when we have left fixed on the right roller bearing. The exact same bridge, we just change the boundary condition and change the left bearing, also the roller bearing. We do get this picture. And just from the look at the shape of it, we know exactly what type of bearing situations we have. And if the bearing is getting blocked, it will change from the right situation here to the left situation. What we also see is the mirrored behavior. So when we have compression on one of the fibers, we have elongation on the other side of the fiber. So that's a rather, let's say, simple case, a controlled environment in a laboratory, very short element. But let us take a look now how the situation looks like on the real bridge.
Okay. So I'm going to present you a real world example. So we're going from the very small scale bridge model to a real highway bridge. So what we have is a kind of big highway bridge in Tyrol in Austria. It's a steel concrete composite bridge consisting out of 7 spans, and it was built in the late 60s. So now it's coming more or less to the end of its lifetime. The bridge is part of the Brenner Highway. Why is it so important? Because the Brenner Highway is part of the E45 route, which is leading from north of Europe till the very south of Europe. In Austria, this route on the Brenner Highway is crossing the Alps. So it's quite important because what you can see here is a very typical situation on the bridge. So more than 2 million trucks are crossing this bridge per year. So it's very important that this bridge is still open and traffic can go over it. We had the opportunity to install several monitoring systems on this bridge, so both static and dynamic sensors. So we have different point-wise sensors, and we also have fiber optic sensors, both statically and dynamically. So we can measure static distributed strain sensing and also temperature sensing, and dynamic we can perform distributed acoustic sensing, where we can assess the vibration behavior of the bridge. How does the situation look like? As already told, the bridge consists out of 7 spans, and 2 out of the 7 spans have been equipped with fiber optic sensors. So we have 2 loops of strain and temperature sensing cables going on the upper and lower part of the bridge beam with a total fiber length of about 800 meters. And what you can see here is at the end of the bridge, there's a rack where the fiber connectors are and where the instrument can be placed. So here you can see where the fibers have been placed. So they have been glued to the structure. And additionally, we have been mounting several point-wise sensors. So for example, you can see an accelerometer in the middle of span 7 and also several prisms mounted for robotic total station measurements. Now I want to show you some results from the static strain measurements. So here we have been using Brillouin analysis, and we are performing quarterly measurements. So what you can see is the seasonal changes caused by the temperature. So we can see in the upper plot the strain measurement, and in the lower plot the temperature measurement, both showed for the lower part of the bridge beam. So you can see in the temperature measurement, so all the data is referred to 0 measurement, that there has been a positive temperature change, which also results in some strain behavior. So at the next measurement we have been performing, this was carried out in autumn, we can see a negative temperature change, also resulting in a negative strain change. At the next measurement, which was carried out in winter, so at rather cold temperatures, you can again see very low temperatures causing negative strain changes. So actually you can see that the bridge is shortening due to the temperature change. So this is actually exactly the behavior we would expect from the bridge due to temperature changes. Additionally, to the quarterly measurements, we have also been carrying out continuous measurements for 2 weeks. So what you can see here is the daily cycle cost by measurement. So again, this plot shows the data for the upper fiber line this time. And you can see in blue the strain measurements and in red the temperature measurements. And you can really see the daily changes caused by temperature, which also results in strain changes. But the strain reaction is somehow delayed by a few hours, referring to the temperature changes. When we have a look on the lower fiber line, you can see a very similar behavior, but resulting in higher strain changes and also in way higher temperature changes. So you can really see peaks in the temperature for the lower bridge part or lower part of the bridge beam, which you don't see in the upper fiber line. So if you now have a look on one specific time in the measurements, you can see the strain measurements here for the lower and the upper fiber line. And you can see the lower line shows kind of an irregular strain behavior compared to the upper line. If we have a look at the same measurement in time for the temperature, you can see a very high difference in the temperature measurement for the lower and upper line, so for the lower and upper part of the bridge beam. So after doing some investigation, we found out that this is resulting from an irregular sun exposure of the bridge beam. So at certain times of the day, only the lower part of the bridge beam is enlightened by the sun and therefore heated up, which results then in a very irregular strain behavior, as you can see at the end of span 7.
Yeah, we are following this bridge since a few years already. And what you can see here now is that just during certain times of the year, we have the special situation that the bridge experiences very strong vertical temperature gradients. And this is something which wasn't really known beforehand, how the bridge reacts to that specific temperature loading situation. However, it's a hybrid bridge. So besides temperature loading, we also have loading due to traffic. And in order to better understand what's really happening when trucks or heavy load is on that bridge, we had the chance to perform several controlled loading tests. And in that loading tests, we had cooperation with the highway operator, our spin-off monitoring company, and a civil engineering company from Vienna. So here the idea was that the bridge is temporarily closed and 2 trucks with a known weight. So the weight of each truck was 54 tons. So we had more than 100 tons that we could place at different locations of the bridge. So we put both trucks on span 6, both trucks on span 7, 1 truck on span 6, 1 truck on span 7. We also had different moving experiments where the trucks were going with certain speed. What we're gonna want to show you today is one specific loading situation. So we just take a look at one setup out of the huge amount that we did there. In this case, we have both trucks on position in the center of span 6. And let us take a look on how the bridge changes when you put 100 tons or more than 100 tons on span 6. So what we have is, of course, vertical downward movement. So the result that we see here is from those total station measurements. So with total stations, we can measure highly accurate 3D displacements. And in this case, we had 3 prisms on span 6, 3 prisms on span 7, and prism targets on the 2 pillar points. So what's interesting to see is that in span 6, we have a downward movement in vertical direction and horizontally and divergence and outward movement. On span 7, although there's no truck positions or nothing happening on span 7, we have an upward movement. And in this case, the bridge deck rises of about 10 millimeters and horizontally, the points are converging. So this is position. But how does such a situation look like in strain? And in order to better understand that, we can now derive strain from those total station measurements. How can we do that? So strain is in essence just a length change divided by base length. And although we don't measure strain directly from total stations, we can calculate strain. So we know 3D position, meaning we can, at the initial situation, we can calculate the distance between these 2 points. Then when we put the truck load on it, the position of both points changes, and also the distance between the 2 points changes. So we can calculate the length change in the end between these 2 points. So when we do that in this section of span 6, what you can see already, we have a positive length change, meaning we also will have an increase of strain. That's just the opposite on span 7. So in span 7, the initial length is getting shortened because of the converging horizontal change of the prism targets. So a negative length change also means a negative strain change. We can do that now for all those distances that we can calculate from between the different prism points. And when we do that, we also get the strain profile along the bridge deck. And what we can see here is we have strain which is in the range between 150 180 micrometers in span 6, and then negative strain, as I said, in span 7. So that works well. However, what we can also see, we have a rather coarse resolution, so we don't see small little details on the strain profile. And that's exactly now where the benefit of fiber optic comes in. So with fiber optics, we can measure the strain directly. And let us take a look now how this strain profile looks in detail. So here we had a high resolution OFDR measurement, and with this we can capture highly accurate and with high spatial resolution the strain profile all along the bridge beam. So what we can see here that both results derived from totally independent different measurement techniques fit very well. But what we can also see is we have some, let's say, artifacts or local deviations in that strain data. It's not really like a peak like a crack would look like, but it's still something remarkable. And here it's interesting to know if this is now regular behavior of the bridge or if the bridge has some issues at those locations. And what's really not difficult is to interpret the result just by looking at strain data. So we do need some additional information. And in this case, it's very interesting to see where are those locations, not in fiber meter, but in geometric location of the bridge. Like often with old existing bridges, you may have some drawings, but the bridges are very often reworked many times, so the old drawings really don't fit to the actual situation. So in those cases, we basically just capture the real geometry. So here with the laser scanner, we can make a 3D model of the real situation of the bridge. So you can see here left the capturing of the data. We set up the scanner at different locations. On the right-hand side, it's just one point cloud of the rather complicated situation of this steel concrete composite bridge. And what we can now do is we can map those fiber optic peaks onto that bridge model. So we have those peaks, and those red circles identified in the strain profile are shown in the spatial location of the laser scan data. And when we take a closer look, we see, all right, we do have all that peaks or that strange behavior exactly at the locations where the bridge girders are connected to the vertical beams. And in the end, this is just regular behavior of the structure. We also confirmed that with the finite element model, where we can also see the same sawtooth pattern in the numerical simulation. So that means the bridge works as expected, but on the other hand, it also means we would be able to identify if one of the connections would get loose. So here we really have the opportunity to identify and localize where the bridge may change its behavior. So that was a lot about the bottom part of the bridge beam. But as Lisa said, we also have the fiber line on the top section of the bridge beam. And let us take a look now on the combination. So how does the strain profile on the bottom side looks like compared to the one on the top? And this is what we can see here. So we can see here, similar to the laboratory simple bridge, we can see where we have elongation at the bottom line, we do have compression on the upper line. So we have that nice mirrored behavior. Here the size is slightly different because the upper beam line is closer to the neutral axis as the lower beam line is like. So, but this is really again the usually expected behavior, because when we have vertical load on a fiber line below the neutral axis, we will have a positive strain. If the fiber line is above the neutral axis, we will have negative strain, meaning compression. So here it's really important to understand how to read those strain profiles in order to make the right interpretation of the result. So that was a lot about static monitoring, but we can also do dynamic monitoring on those real bridges.
So I'm going to present you how the dynamic strain behavior of the bridge looks like. For example, how the structural reaction to the ongoing traffic looks like. So therefore, I'm going to present you some results from the distributed acoustic measurements, which enables the measurement of the dynamic strain behavior. So what you can see here is in this waterfall plot, on the first part, the upper fiber line, and on the second part, the lower fiber line. And what you can see is just ongoing traffic. So you won't see a lot at the first part, so the upper fiber line, but as already the other results have shown, on the upper fiber line or on the upper part of the bridge beam, there's just less going on. So on the lower fiber, you can see traffic going on, and for example, right now, a very strong signal caused by a passing truck. So again, you can see here in the first part, the upper fiber line, and in the lower part, the lower fiber line. So what the distributed acoustic sensing measurements enable is the measurement of high frequency changes, for example, traffic flow. So we can not only identify moving vehicles, but we can also estimate the velocity of these vehicles. So for example, here you can see a passing truck with a velocity of about 76 kilometers per hour. And if we have a look on the signal, we can also distinguish between a moving vehicle, for example, as a car, or a passing truck. What we can also do, since we have very high frequency measurements with up to several kilohertz, we can have a look on how the dynamic strain behavior of the bridge looks like when the truck is passing the bridge. So in this video, please have a look on the truck and the yellow circle. And on the right side in the video, you can see the dynamic strain behavior of the bridge. And the moment the truck enters the bridge, you can see in span 6 a positive strain change, and at the same time a negative strain change in span 7. So now, as the truck is entering span 7, you can see just the opposite behavior. So a positive strain on span 7 and a negative strain in span 6. And as the truck is leaving the bridge, the strain is going back to more or less a zero line. As already mentioned before, we do not only have fibers at the bridge, but we do also have some point-wise sensors. For example, we mounted prisms for total station measurements, as we have just seen before. So what we can do now is take one point for the fiber and compare it to the total station measurements. So for example, we take a point in the middle of span 7 for the lower part and compare these measurements to the total station measurements. So at the first sight, you can see the results fit together quite well. And if you have a closer look, we can see that the results really fit together well, and the peaks are caused by passing vehicles or trucks. But what we can also see is that the sign of both measurement techniques is just opposite. This can be explained with the same semantic representation we already had before. The truck passing the bridge is causing or is acting like a vertical load on the bridge, which of course results in a settlement of the bridge deck, so a downward movement, but at the same time it results in a positive strain for the lower fiber. And this is exactly what we can see here. What we can also do is, since we have high frequency measurements, we can do some frequency analysis. So what we see here is a frequency analysis for one point at the fiber for the lower fiber line in the middle of span 7. We can see the main frequencies of the bridge between 1 and 2 Hertz, and can compare this to the accelerometer we have mounted at the same point on the bridge. So we can see the results fit together quite well. But one of the main advantages of distributed fiber optic sensing is that we can do the frequency analysis not only at one point of the bridge, but on every point along the entire fiber. So for example, we can also have a look on the frequency behavior of the bridge just above the pillar. what we can see here, if we take a look on the appearing frequencies, the main frequencies are moving upwards a little bit. So the main frequency is almost at 2 hertz now, and the frequencies are quite damped compared to the middle of span 7. So if we have another look on a part of the upper fiber line, again in the middle of the bridge span 7, we can see that there's almost nothing going on compared to the lower fiber line. And this is just the same result as all the measurements before have shown. So if we now have a look on those 3 frequencies, which are circled in red here, what we can do with distributed acoustic sensing is that we assess the vibration behavior of the entire bridge, or at least where the fibers are mounted, so along the entire fiber lines. And what you can see here is now the behavior of those 3 frequencies, the amplitude behavior along the entire fiber. So in blue, you can see the lower fiber line, and in pink, you can see the upper fiber line. And you can see the frequency behavior along both bridge spans. And this is just as expected. So above the pillar, the frequencies are really damped with very low frequencies, and the amplitudes increasing in the middle of the bridge spans. And what we've also seen several times already, that the upper part of the bridge beam is moving way less than the lower part.
Yeah, so far we've talked about existing bridges, and as I said in the beginning, this is really a major issue. We want to keep them in service as long as possible in a safe way. However, at a certain point in time, we have to replace them. And this gives us now the chance to also embed fibers into newly constructed bridges. And this is now one example that we are heavily involved at the moment. What we have seen also from the data so far is we have taken a look at slow changes due to temperature. We have taken at constant or static vertical load. And we also have taken a look what's happening when trucks pass by. But at this bridge, we had the chance to perform also measurements just at the time when it was finished, but not open for traffic yet. So you have entirely completed bridge where we have, or where fibers were installed during construction, and now we can make dedicated controlled excitation experiments. So the idea was, in this case, we have the fibers embedded into the concrete, so not surface mounted anymore, directly embedded into the concrete. These are in the first span of the bridge, and there's again one fiber line at the bottom of the bridge and one fiber line in the bridge deck being integrated. So this is now concrete, full concrete bridge. And now in order to excite that, we can do static loading tests, but also dynamic loading tests. And for those dynamic loading tests, we can put a shaker on top of the bridge. So you see the bridge is almost finished already. So the asphalt is there, everything is done. And now we do have the shaker here. And with this shaker, we can apply vertical force. And this shaker is then performing vibration or inducing vibration. And the shaker can be controlled in different ways. So we can change the amplitude, but we can also change the frequency of that shaker. Obviously, it's a newly constructed bridge. So we have highly accurate numerical models, and the idea is to see how well does the real construction fit to the numerical models. And for the sweeping, we can then take a look where the actual eigenfrequency of that structure finally is. And here just some results. What we can see here is 3 different actions. So we can see first 2 inclined lines, and these 2 lines are frequency sweeps. So in this case, the frequency of the induced vibration was changing linearly. So we can see that the frequency changes over time, and we can also see well how well that maps into the fiber optic sensing data. So what you can see here is, so this is some results from distributed acoustic sensing measurements. So the idea was of those sweeps to identify the eigenfrequency. And when you know the eigenfrequency, what we can do then is just keep that frequency and excite that bridge deck at its eigenfrequency and changing now the amplitude. And this is now happening here in the second part. So here the frequency is kept constant, but the amplitude is being changed. And all of this helps to understand the dynamic reaction of the bridge. So additionally, by having frequency sweeps and amplitude sweeps, we also had white noise generated, and this resembles then a typical traffic situation. So we really can do a lot with fibers when bridges are constructed anew. So we can assess if there are any problems occurring to construction. We can also assess how well the final construction fits to the design or numerical computation. And as we have embedded fibers, we also want to use that fibers for the long-term monitoring of bridges. And here one usual question then arises, and that is, does fiber optic sensing even work as long as bridges live? So bridges live for several decades. And if you want to use a sensing technology for the whole lifetime of a bridge, it has also to survive several decades. And here I can tell you also a little bit about my personal experience. So this is a monolithic concrete bridge that I have equipped more than 20 years ago. So you can see here the installation of fiber optic sensing cables. And just recently, we went there again with our students. And from my personal experience, I can say it definitely works at least for 2 decades, because that's what we have installed more than 20 years ago, can be still used today. And we are looking forward to continue measurements, not only on this bridge, but on the other bridges that we are monitoring as well. Yeah, so this brings us almost to the end of our talk. But we just want to add a few more comments before we finalize. And what's so fascinating for me is that with one fiber, you can get so much information. And we wanted to show you this on that one example of the hybrid bridge in Tyrol, because here it's the same fiber, but depending on now what type of instrument or sensing technology we use, we can get so different information. So for high definition fiber optic sensing, we can have an understanding of bearings are being blocked. Like with the OFDR, we can see if local strain behavior, how this is reacting. So we did show you how the connection between the bridge girders and the vertical beam works. We can also use that for crack detection. When we use Brillouin sensing techniques, we can take a look at long-term strain and temperature changes. So slow changes due to the seasonal or daily variations of temperature. When with that, we can take a look on how the dynamic reaction over the whole bridge looks like. And with this, we can not only say how the bridge reacts, but we can also have an understanding what's happening on the bridge. So we can see the traffic flow. We can see how many trucks are passing by. We can see how fast those trucks or cars are. And we can take a very close look to the frequency analysis and see where the actual eigenfrequencies of those structures are. One important point to note is then, we always said we are measuring temperature or strain. But at the end, we send light into a fiber and we work with the back reflected light signal. And as it is light, we cannot measure the temperature strain directly. We measure some quantity or parameter of light. So we can measure the frequency, we can measure the wavelength, we can measure the phase, we can measure the intensity. And we have to relate this raw measurement to the unit that we're interested in. So we have to know the relation between our core measurement unit to the desired measurement unit. And this needs calibration. And this is also something that we are focusing on, because it doesn't help you much when you can measure frequency changes highly accurate when you cannot derive correctly a strain reading from that. And in order to assess those relations, we have certain setups in our laboratory. And here, this is a measurement laboratory designed for geodetic and fiber optic sensing instruments. So we really have a very good situation that we have a temperature controlled environment with foundation isolated main testing facilities. So although maybe the walls may vibrate, the core facilities are isolated. And here we can do static strain calibration, temperature calibration, dynamic testing, and we can also perform long-term evaluation of sensing systems. And from all those results, we just want to show you 2 different things. So the first is we also have a setup here to assess the performance of distributed acoustic sensing units. So we have a setup here according to the C-form standard. And here the idea is to have a very long measurement line. In our case, it's 40 kilometers, and we can excite the fiber at 3 different locations. So in this case, our first stretcher is about 250 meters after the instrument. Then we have a delay loop of about almost 20 kilometers, another stretcher about, again, 40 meters long, then another delay loop about 20 kilometers, the third stretcher with 40 meters, and then a final loop with about 260 meters. And what we're doing here we can take a look on the noise of the instrument. So one example that you can see on the right-hand side, here we can see when we take, for instance, a look at the red curve, we can see how the noise behavior looks like in different frequency ranges. So we can see that depending on what frequency we are looking for, we have a different base noise. What we can also see is now when we take a look at the blue, red, and yellow line, we can also see, as expected, that the noise is increasing with the distance. So the further our signal is away, the more noisy it is. What you have also seen is that we are talking about very weak signals, but also when a track passes by, the signals can be very, very strong. And in this case, it's important to understand the dynamic range of the DAS instrument, because if a signal is too strong, the instrument goes into saturation and cannot follow that signal reliably anymore. And this is what you can see on the top right-hand side. So this is dynamic range result, where we can see we increase the amplitude with time. And so in red is the excitation signal. So that's really how the shaker, the stretcher is vibrating. And in blue, we can see the result of that specific DAS unit. It can follow it for a rather long time. So let's say after 25, 27 seconds, but at that time, then the phase rate change is too big and the instrument cannot follow it anymore. So it's also important to understand then and to have a feeling how well or what will work then on the real side. So that's for the dynamics. Just a few comments to static. For static, we can also stretch different fiber optic sensing cables. We can stretch bare fibers. And here we are looking on the relation between the, let's say, frequency shift, wavelengths change in case of FPG sensors with respect to the real applied strain. And on a broad scale, everything looks linear, but when we zoom in, we can see, for instance, that we have here certain run-in effects, we have certain cycles, and here it's important to really derive the right calibration in order to transfer then your frequency shift to an accurate strain reading. So these are just some comments to the end, but overall, we really want to bring across that fiber optic is a very useful tool for bridge monitoring. It's not only beneficial for existing structures, but are also well suited to assess new structures. What's so good about distributed sensing is that we can localize structural failure. So very often it's also about detecting and localizing a failure. Here it's important what we wanted to get across. It's not about just to identify at what fiber meter something is occurring, but also to know where that fiber meter is spatially on the structure. What we also wanted to get across, fiber optic sensing is a very great tool, but sometimes it's not the only solution. So from our experiences, what works best is when you combine distributed fiber optic sensing with other sensing technologies in a smart way. And as I said, calibration of sensing cables is crucial to deliver reliable results. What our goal is also to promote fiber optic sensing so that it becomes a standard solution in tenders, and therefore we are heavily involved in the development of standards and guidelines. And where we also want to contribute, and we hope we are successful by doing so, to make case studies and really show that it's a mature technology, and when you know what to look for, you can have a sensing solution that works for several decades. So that was just a short glimpse of what we do. If you want to know more, we also have here just a list of some of our applications, so feel free to take a look at them or just contact us. And with all of this, we want to thank everyone very much for listening to this webinar, and also for FOSA for inviting us to give this webinar. And this basically ends our webinar, and thank you very much for your attention. And Lisa?
Thank you for your attention, and we're happy to answer some of your questions.
Well, thank you, Lisa and Werner. We've got quite a few questions. Let me kind of lead off. One of the slides referenced the use of the fiber for traffic monitoring. We wondered if you could elaborate on can that be used, for example, for detecting traffic jams and sharing information with transportation authorities? And is that a use case that you're envisioning as being part of the solutions that are installed?
Mm-hmm. Yeah, that's definitely something that we're looking for, because as you could see here on that one of the slides, it's very often we have the situation that trucks are jamming up at that bridge, and that's obviously one of the worst situations where you have a very high load on that bridge. And yes, we can identify traffic jams in the signal because with different ways. For instance, with DAS, you see then suddenly then you see moving trucks, and you can also see then how they get slower, and in the end how they stop. And when they just stop and static, you don't see any vibration signal anymore. So you have to take a look at the history of the vibration signal. That can help you to understand if traffic jams are piling up. And that's something that we do there. And what's also interesting for us is then, you know, a question that we're looking for: can you actually determine the weight of the trucks which are on the bridge or crossing the bridge? And in this situation on that highway, there is also a central station where the weight of all trucks is being taken. But unfortunately, this is a few kilometers down the road. So until the trucks arrive at the bridge, they may have changed the order of the trucks, but we're still trying now to take a look of how well we can calculate the weight of the trucks from the fiber optic sensing data.
So next question, we have two related questions for concerning installation, and sort of the first part of it is, do you use loose fiber or tight fiber? And secondly, do you use conduit, or do you have a preference for conduit, or do you use it exposed?
Mm-hmm. Okay. Do you want to answer?
Yes, so for this example of the highway bridge, we're both using a strain and a temperature fiber. Like they're really connected to the steel beam, so they're glued to it. And of course, the strain fiber is like a tight fiber, and the temperature fiber is able to move in order to only be affected by temperature and not by strain.
Yeah, so this is about static strain measurements. Regarding dynamic strain measurements, this goes back also to the saturation of your instrument. Because here, normally you would say you want to have a very good bonding, but it could be then the strain transfer is so good that you have such a high strain rate that the instrument may go into saturation. So sometimes it's better than to have a more or less loosely coupled or a fiber which is not so strongly linked, so that you dampen that transfer a little bit on purpose, so that the instrument does not go into saturation. And maybe regarding cracks, if you want to go for crack monitoring, you have it tightly coupled, because otherwise you would not be able to transfer the crack to the core of your fiber.
So the next question is, do you need special fiber, or the reverse is, can you use existing fiber as well that may be going through the bridge?
Yeah, so this goes back to what you're interested in. So it doesn't work for crack detection, but regarding traffic, we also do a lot with existing communication cables, not only in bridges, but also just which are installed under the road or close to the road. Yes, so therefore you can also use communication cables. If you want to have really, let's say, bending and curvature or cracks, then you need special sensing cables.
So can vertical deformations be measured with DFOS?
Yeah, so basically here we did go the other way around. So here we did show you vertical deformations and how we can derive strain from vertical deformations. When we go the other way around, it's theoretically possible. Also, what you can see here on that slide here, we have here a fiber at the bottom and at the top. So when we take a look at the difference of the strain, and we know the distance between the two fibers, we can derive the curvature. So that works well. In order then to get the displacement, we have to double integrate. And here the big issue is we have to know the boundary conditions. So very often people just keep the first and second point stable and then start double integrating from them. And that could lead into problems when your first and second point are not stable in the end. But here what's nice is we can combine those fiber optic readings with the total station measurement. So basically the total stations can provide you point-wise those boundary conditions. And with that, you can solve then the unknowns of the double integration. And I think here both systems complement each other very well. And we've done a lot with that in tunneling, for instance.
So a related question is, how do you decouple strain from temperature measures on a single fiber? So I guess you can probably elaborate on how those two technologies work together.
Mm-hmm. Yeah, so what we tried to show you almost everything that you can connect to a fiber. What we haven't shown you is Raman measurements, because they are mainly temperature dependent and not strain related. We also do Raman measurements as well. But here the purpose on that bridge was from the beginning also to try out to see how DAS works, and therefore also to see how DAS works with the tightly coupled and the loose fiber. But yes, we could in the end, it's also possible when you take readings with an effect that is only temperature dependent, and then with an effect which is temperature and strain dependent, and trying to decouple that. And I know there are also some people who are making investigations if this is possible just with Brillouin measurements only. So if you have something or an instrument or something to try out, we have nice structures, and we are happy also to see or to work together with you to see how those or your solution works on those structures.
So you did a great job of showing sort of your history long-term of reliability or of installation of fiber, but what happens if instruments breaks during long-term monitoring, and how do you detect that, and how do you respond to that?
So what is really important is to have a reliable zero measurement. So for example, if you have a new bridge, as we have been shown before, so where the fiber is directly embedded, it is really important to have a zero measurement, and to also like do some kind of zero measurements from time to time where you can also connect those measurements. And what we are usually doing is that we are doing measurements with two different DFOS techniques. So in order if one instrument breaks, we can still use the information we have been sending with the other instrument or the other fiber optic technique. So in order to be still able to perform the long-term measurement.
Yeah, maybe I can add a little bit to that. So one thing is, if an instrument really breaks, if it can connect your measurements with a different or another instrument. The other question is also, are you able to detect if your solution has a sort of drift in your data? And this is what we also take a look at long-term monitoring. So although we may have an instrument there which is measuring permanently 24/7, we dare then go once per year with a different instrument and make a measurement with that instrument just to see if the both solutions match. And another question is regarding cables also. Are we really sure that our cables don't have any creeping effects over decades? And therefore, we also, when we install fibers, we cut off certain sections and keep them in the laboratory and pre-strain them. So here we have fibers pre-strained at a constant strain or different strain levels in the laboratory, and make comparison measurements on a regular basis.
The next question is, do you recommend distributed optical sensing for pavement monitoring? As always with our webinars, people are looking for extensions of the application. So let's try that one and see if that's a possibility.
Yes, we do. And we also are preparing now a test setup where we have working together with a highway operator to have a test installation in a test field where we can embed the fibers into pavement. And here the idea is to apply controlled load to see then also make some traffic jams, all of this, but also to make some controlled potholes and to see then how well we can detect them, and if we can maybe say something about the size and location of that potholes. Because what's important also is with the fibers, we know very well where the signal is along the fiber, but do we also know how far sideways of the defect is? So that's something that we're investigating there. Yes, it's definitely something that's worth looking for.
Next question is for 3D scan versus DSS. What was the spatial resolution of the interrogator?
The spatial resolution, so the spatial resolution, I think it was about either 2 point something millimeters, or I think 5 millimeters or 1 centimeter. I cannot, as I said, it was in the millimeter range for the distributed sensing.
Well, I think that's it. We have a few other questions, but I would encourage them of a more technical nature, but I would encourage folks to reach out to you. And as always, we get a question about when will the presentation be posted, and we expect hopefully later today, but it will be part of the very valuable library that FOSA has of presentations on our YouTube page. And so I would encourage people to take a look at that. Lisa, Werner, thank you very much for a very informative presentation. And this concludes today's webinar.
Thank you very much. Have a good day.
Thank you very much.